Logic operators and logic gates both appear extensively in computers and computer science and computer engineering. Uh, Computer processing units, computer circuits, CPUs, etc., are built out of a variety of logic gates. And in programming languages, we often use a lot of the um, logic operators to do comparisons, etc. So understanding how the different logic operators work is important. There are a list here of the basic logic operators. Each one has a different truth table. On the right-hand side, we have truth tables associated with these different operations. So the first one is OR, meaning that truth can occur if either condition is true. So either this or that. That's a colloquial use of the logic operator OR. And in a formal sense, if either input is true, then the output is true. So that's the definition of OR. So here is, and you'll notice that I'm using the 0 to represent um, false and 1 to represent true. That is a pretty common, or that is the standard for um, digital circuits. So 0 is equivalent to false, and 1 is equivalent to true. So false, here we have input A is false. Here we have input B is false. And therefore, if either A or B is true, then the output would be true. So 0 false and false or false is false. True or false is true. False or true is true. And true or true is true. So there's the truth table for OR. If either input, regardless of whether both inputs, but if either input is true, then the output is true. And requires both inputs to be true. So in a colloquial sense, you might say this and that. You know, it's a condition where you want both things to be valid. So false and false is false. True and false is false. False and true is false. And false and false, or sorry, true and true is true. Because both conditions are true, therefore the and is true. Not. Not is an inverter or changes the state from true to false. And I have a couple extra rows in here. So what is the opposite of false? It's true. And what is the opposite of true? It's false. We don't really need those two rows. Um, XOR is an exclusive OR. So it's like OR, but it says that um, either one can be true, but not both. So XOR is either one, but not both. So false and false is still false, because neither of them is true. Either the A or B is true, so that's a true. Either A or B is true, that's a true. But here, down in this row, you'll notice that either A or B is true, but not both. Well, here, both of them are true, so the end result is false, exclusive OR. The last two, NAND and NOR, are both knotted AND. So NAND actually means not AND, which means you do an AND gate logic and then not the output. And NOR is the same thing as knotted OR gate. So one thing we can do is we can go down the truth table. So I'm doing in NAND. So I go up here to the NAND gate and I say the output is originally 0, so I knot that. So what's the opposite of a 0? A 0 becomes a 1, and so I get 1. The truth table for this one would be 0, so this becomes a 1. The truth table for 0, 1 is a 0, it becomes a 1, and the 1, 1 in the AND is a 1, so it becomes a 0. It's the it's the inverse of the AND gate. And the inverse of the OR gate would be, we'd look up at this table, the OR table, and we go down and turn zeros into ones and ones into zeros. So this becomes 1, 0, 0, 0. Those are the basic gates that are used extensively in digital circuits to build all sorts of complicated circuitry, adders and memory locations and flip-flops and a variety of things that go together to build things like digital computing circuits like CPUs and arithmetic logic units, etc.